controversial subjects with the facts can be tense, but we are a sub-science here to make things make sense.
Hello, Katie Mack.
Hello.
How's
How
it
are
going?
you?
Thank you so much for coming on the pod.
I'm very excited to be here. Thank you for inviting me.
Okay, I just have to say that we received these books only last night. Your new book, The End of Everything, Astrophysically Speaking.
Yes.
And I genuinely could not put it down. It is so well written about something like physics, which is, hard for a lot of people to grasp. And also, I really want to say that it's like beautifully written. It's hilarious at times. The diagrams are incredible. I literally have a note beside one of them that's just, oh my God, wow. It's like,
It's taking notes.
I don't know. It's one of the beginning ones where like time's going this way and it's like showing how you can see into the past through space. Like just an incredible, incredible book. So first of all, I just want to say congrats.
Thank you so much. I really appreciate that.
And now we're going to ask you things like, so how did the universe start?
Okay.
Yeah, I want to just say we actually randomly met. I guess it was like 7 years ago or something,
It
right?
was so long ago. Yeah.
like
It was
when
in Australia.
Yeah, so for people listening or watching, we had gone down to this sort of science event down in Australia, and we didn't know most of the people that were there. We were just like on a whim, like, okay, we'll go to this like science thing that's gonna go around Australia. And I was just like, it's so random that since then we've known you. You've been on Twitter. we've kept in and out.
Yeah.
But yeah. How's it been? How you been since 7 years?
Oh gosh, I've been good. Australia was great, and I moved back to the U.S. a couple of years ago, and I'm at NC State University now as an assistant professor, and I'm part of their Leadership in Public Science cluster, which is this cool initiative to bring in people who do science that's somehow connected to the public. So either through like citizen science or somehow like public engaged science where you talk to people as part of your research, or science communication, or in my case, I do physics and then I talk about physics. And so that's kind of that's my connection to public science. But it's great because it means that I get to do public outreach as part of my official faculty job, which is a very rare thing to be able to do as a researcher.
Okay, so let's reach out to the public with some physics. I'm literally obsessed with this book. Okay. What made you become so interested in like the end of everything? Or as it's put here, eschatology? Is that a real thing?
Yeah, eschatology is the real word for the study of the end of the world.
Oh my gosh, I'd never heard that before. That's so good. So you're an eschatologist?
It's sort of, yeah, I guess so.
Is it the study of the end of the world or the study of the end of the universe, or does it matter?
Well, so it's the study, you might call it the study of the end of creation. So it's a word that derives from a kind of theological concept of, Armageddon, basically. So eschatology is about like how everything's going to end. And in the initial sort of formulation of that idea, it was about the end of the world because that's what people knew about. But you can apply it to the cosmos, and there are physics papers that use the term eschatology to talk about the end of the universe.
Whoa! So when you started studying physics, was that something you had general interest in, or is it something like through the years that you kind of found yourself falling into?
More the latter, yeah. So I've been studying physics for a long time, and I've been interested in cosmology in general, which is cosmology is just the study of the universe as a whole. So how it changes over time, the beginning, and what we can learn about that, and like how galaxies form and stuff like that. And it also includes the end, what's going to happen in the far future, and that's something that I've been gradually becoming more interested in over time, just because, I don't know, it's a fun thing to think about, like what will happen in the cosmos in the future, what will it look like, how will it all be destroyed in the end, that kind of stuff is fun to contemplate.
I literally get butterflies in my stomach talking about this. I don't know, I just find it so compelling.
Well, you also have a really interesting relationship to death and stuff that I wonder, not to like put that out in the world.
Okay, well, we can. I wanted to save it to the later, but we can get into it
no,
now.
we can get to that because I also wanted to quickly point out, like, for people watching the video form of this, Katie has like physics equations behind her on a chalkboard, which were authentic. We talked about before the pod. Will you let the audience know what is actually written behind you?
So I was just in a meeting with a student via Zoom, and I have a chalkboard, and the chalkboard came about because I was going to do a public talk via Zoom, and I needed like visuals, and I was working with the people at Perimeter Institute, which is where I'm kind of visiting now, and they suggested a chalkboard rather than trying to put together slides and stuff like that. So that sounded great. Awesome. So I used it for the public talk, and now it turns out it's also really great for having meetings with students and explaining equations and drawing.
Turns out it's this great explaining medium that.
Yeah, it's a really useful thing. Yeah, so I was meeting with a student and talking about dark matter and the annihilation of dark matter and how it can put energy into the universe through this annihilation power. I can explain dark matter later if you want. But
that's the equation. I know that equation. You don't have to tell me that. I know that.
These are equations from a paper I wrote in 2014 about how dark matter annihilation can produce radiation in the cosmos over time.
Okay, so we're going to help our listeners by going a little bit into order because your book does start with, just the beginning of everything. And so at one point it says the Big Bang didn't happen at a single point, but at every point.
Yeah.
And also in the beginning there was singularity. I was wondering if you could just like you know what I mean? Like talk about that. Sure. What does that mean?
Yeah. Okay. So when people talk about the Big Bang, usually what people mean when they talk about the Big Bang is this idea that everything started at a single point called a singularity, and then that somehow exploded and then created all the space and time and stuff that we see out in the universe. And that's an idea that comes from like you look at the fact that the universe is expanding. Right now, galaxies are getting farther apart. There's more and more space, and you just take that expansion, you dial it back, and you get to this idea that the universe was, smaller in the past and more compressed. And then if you take that to an extreme, then you get to the idea that the universe was like a single point, right? And that singularity is a popular way of talking about like the beginning. We don't now think that necessarily a singularity happened because, well, for one thing, it's very hard to study the very, very beginning in such a way that you can get to that. But also we think that there was a time in the very early universe, in the first like tiny fraction of a second, when there was this rapid expansion phase. And that really rapid expansion phase, which we call inflation, would make it very hard to know what happened before it. So we don't know that there was a singularity. But if there was, it didn't have to be like a single point. It could have been a kind of state of infinite density everywhere in a large space. So like the universe could be, infinite in size, but there was a time when it was like infinitely dense as well. But what we really know, what we mean when we say the Big Bang theory is we mean that that the universe was hotter and denser and in some sense smaller in the past. So it is just a matter of taking that current expansion, dialing it back, and you get to a hot, dense state. And if that sounds familiar, the TV show The Big Bang Theory, the start of the theme song of that is actually a really good encapsulation of the Big Bang Theory. So it goes, the whole universe was in a hot, dense state, then nearly 14 billion years ago, expansion started, right? So like that is actually what we mean when we say the Big Bang Theory, that the whole universe was hot and dense, and it was everywhere in the universe. It was hot and dense because there was this, it was in this sort of more compact, more compressed, hot, dense phase. And then as expansion happened, that cooled the universe. It kind of spread out all this radiation and all this energy and all the matter. And that created the conditions for things like, galaxies to form and stuff like that.
Oh, it's so cool. I like to self-identify as someone who's hot but not dense. So I do relate in some ways.
Okay. I'm so curious, like when you talk about or study or communicate physics, For me,
Yeah.
does it bring you to? Do you have to put yourself in sort of another plane of thinking almost? Because for us, I mean, like I kind of measure myself most with like biology because I can like relate so much to it and I feel like it's here. And even when I get down
Yeah.
to like the biochemistry, I still feel like, oh, well, it's inside me. But sometimes when I'm not very educated in physics and I hear you talking, I'm like, oh my gosh, this is like literally a whole other world that it feels so
Yeah.
detached from what I experience. So I'm curious, like for you as someone who knows so much about it, what does that feel like?
I mean, I've been swimming in this stuff for years, so it doesn't always seem otherworldly to me, but every once in a while, you have to think about the kinds of scales of the universe that are utterly inconceivable. Like you just cannot fit that in your brain. You have to think about like quantum mechanics, and you have to think about like these weird mathematical relationships between things, and then when you're thinking about like the early universe, it's all about like the subatomic stuff that's going on, and so that's also scales you can't imagine, and processes that are happening so fast or in such a weird environment that you can't really conceive of that. And so you kind of get used to doing all these mental tricks around like timescales and length scales and mathematical relationships between things, where you have to find tricks to visualize stuff that and it's you just kind of create these toy models in your head of how stuff works and go with that. But if you actually stop and think about what you're actually thinking about, like what you're actually trying to describe, it can get a little overwhelming. I mean, I have a bit in the beginning of the book about the first time that I really thought about how the process of inflation worked, and this idea that at the very beginning of the universe there was this rapid expansion of the whole universe, and that changed the structure of space basically. And we don't know why that happened. We don't know for sure that can't happen again right now. Just the idea of being at the mercy of these huge forces, and later in the book I talk about vacuum decay, which is one of the possibilities for the end of the universe, where there could be a kind of bubble of a new kind of space that just forms somewhere in the universe. It expands out at the speed of light and destroys everything. We have reasons to believe that processes kind of like that might have happened in the very early universe, and then you're like, we are nothing in this universe. We have no power over this. We're governed by things we do not understand. And then it's a little bit intimidating.
Seriously, yeah.
Are you mentioning the part you actually recently were at an event and you talked to me about this, and I thought about it for days. Is this the same thing that you were saying, where you first sort of learned that at any moment the universe could end? That's what you're talking about?
Yeah.
So that was explained to you by someone like a professor or something like that, right? And what is that?
Yeah.
What did that do to your like psyche? It sounds like it had a big impact on your life.
It shook me. Yeah. No, it's I mean, I talk about it in the intro of the book because it was a moment of it was kind of a scary moment, It's kind of like, oh gosh, this is something that's a big I don't know. Like we get used to, the kinds of stuff we deal with every day. We get kind of used to the idea that everything is kind of solid, and we know how it all works, and we can control our lives in some way. And the idea that actually, the reality of the universe is governed by much more abstract stuff that we don't have any control over. We maybe can't even see, and processes that happen. Maybe they happen over billions of years, and so they don't really affect us now. But if you think on those timescales, you end up with the idea that like none of this is permanent. None of it is anywhere near as solid as we think it is, and
so
we're just these kind of temporary blips.
I was going to say, does that as a result sort of inform a personal philosophy, or like not spirituality, but obviously it impacts the way you view life and the meaning of life, and like
a little bit. It's hard to articulate exactly, but I think Well, it took me about 2 years to write this book. And so I've spent about 2 years totally, enveloped by thoughts of the ultimate end of all creation, right? This is maybe not the healthiest place to hang out. You can't spend time there and not think about it. And in fact, at the end of the book, there's an epilogue, which is just a short section of mostly interviews with other physicists and astronomers, where I basically went around and I asked them about like what they think we're going to find out in the next few years, how this field is going to develop. But I also made a point every time to ask, so how do you feel about the end of the universe? Like, how does the end of the universe make you feel? Like, what goes on with you emotionally? And I got lots of different answers. Everybody had some different perspective on it. Some people said, it makes me really sad. I don't like to think about it. Some people said that they don't think that can be the end of the universe, that these ideas that we have about what's going to happen, like surely we'll have something better will come along. And some people were like, oh, I think it's great. I think it's awesome that we're just temporary. Like that's how it should be. So, a whole range of reactions to this, and my own reaction to it. I think I'm still kind of figuring that out. I think I've never been somebody who's been comfortable with the idea of death. That scares me, and I don't like it. And I have not come to terms with the idea that I'm going to die someday. And the idea that the universe is going to die someday, I don't know what to do with that, especially if you think about it in terms of what does this mean for your legacy? What does it mean for the legacy of humanity if we all, if at some point it's not going to matter that we existed because the whole universe is going to end? Like, what do you do with that? And I think that in the process of writing this, I've definitely had to find ways to kind of reconceptualize existence so that it has some intrinsic meaning that doesn't depend on how it ends. That doesn't depend on some externally constructed, right. It was all for good, I don't have to rely on that because it doesn't seem like there is going to be, everybody at the end, everybody kind of comes together and says, well, this was nice. This is, we're not going to get that. So I might as well try and find some way to be like, well, this is what we have and we have to enjoy it. We have to, make the most of it while we're here.
I'm going to read something from your book, that you wrote, because I thought it was, I think it's a good example of how I really think that you're a beautiful writer. And I also think that you're really funny. And I know I keep saying this, but I personally, Mitch has said, I have a lot of death anxiety. I read a lot of physics books similar to books like yours because I have a hard understanding of it, but I do kind of find it spiritual. And I find it, I just find it to be the most fascinating thing in the world. Fair enough. You talk on those scales, on this earth, the most fascinating information. So I'm just going to read this because to me, I kind of found it comforting. So it's there's something about taking the opportunity to wade into the cosmic perspective that is both terrifying and hopeful, like holding a newborn infant and feeling the delicate balance of the tenuousness of life and the potential for not yet imagined greatness. I think that's beautiful, really nice. And I think it's kind of spiritual. Oh my god, I'm literally tearing up. But I really think that is so I have a lot of death anxiety, and I also was thinking about because I also later last night had a bit of an edible, kept reading the book, and I realized I have a relationship with this type of science and physics similar to I kind of do with weed, which is this delicate dance of anxiety and excitement. It's I can't think of anything more exciting than talking about these things, but it always comes with this meeting of anxiety, and it's just a thrill. And I think one thing about your book that I really enjoy is the humor, because sometimes it can be so hard to take in this information. In a lot of other physics books, they don't give you any breath of fresh air, and sometimes you shut the book and you stare at the wall and you're well, what is the why am I even trying to be a good person or something like that? Where I think that there is enough in here, and I think even sentences like that make you realize no, there is obviously there's not obviously a purpose to life, but it's important to take this
that
information.
Perspective is really nice, yeah.
And another positive thing that I want you to maybe speak on a bit is that truly, like, yeah, like we're going through a global pandemic. You know, America has like one of the worst presidents in history. There's a lot of bad things going on, but it sort of is like the best time to be alive for physics. And I thought that was an interesting perspective, just being like, I think a lot of people are looking for some place to find hope. And it's like, well, actually, you're on the cutting edge of like this type of knowledge.
Yeah. There's a huge amount going on in physics right now. And it's a really exciting time because we have these big mysteries, right? And we don't know what, we don't understand a huge fraction of what the universe is made of. We don't understand, how to fit together things like quantum mechanics and the theory of gravity, general relativity. We don't understand particle physics in a certain way, and so there are these big mysteries. But we know that there are answers out there, and we're hopefully really close to getting them. So for each of these mysteries, we have some clue that there's a direction we can go where we can figure it out. And we have some amazing telescopes coming up. We have amazing experiments happening. And I'm hopeful that we're gonna get somewhere with that.
Okay, I have a question that I always like to ask physicists. So this concept of like quantum mechanics not working with the theory of relativity and gravity.
Right.
What exactly does that mean? It's like the math doesn't add up, but the experiments do?
So what it means is that there's no way to put together what happens in relativity and in general relativity, the theory of gravity, and what happens on a particle level in quantum mechanics, particle physics, and have them be consistent in situations where both of them should be important. So usually they're not both important. Usually if you're dealing with general relativity, that's the physics that governs very, very massive things like black holes and, planets and the shape of space-time on large scales. And in those kinds of situations, it doesn't matter what's going on with particle physics because like the particles are at such a different scale that you can ignore them completely. And when you're dealing with particle physics, particle experiments or electron, or figuring out what electrons do when they scatter off of molecules or whatever, like gravity is totally unimportant because these things are so light that they're doing nothing at all interesting to space. They're just there, and you can ignore gravity totally. But there are situations where you have to figure out how to bring the two together. So when you think about what's going on at the edge of a black hole, for example, we think that there are quantum processes that happen at the edge of a black hole that allow radiation to come off the edge of the black hole called Hawking radiation, and that allows black holes to evaporate over time. And there's no good way to bring together the particle physics and the general relativity in that context that is perfectly consistent. So, for example, if you, as the black hole is evaporating, it should be producing a kind of radiation that's determined really just by the kind of shape of the space-time it's in, the what's going on in the space around it. But that means that you could throw a whole bunch of stuff into a black hole and then wait for it to evaporate, and you wouldn't know what you threw in because the radiation is just determined by the mass, and the mass, it doesn't contain the information of what you threw into it, just the amount of stuff. And quantum mechanics tells you can't destroy information. Like there are rules about that, and so there's this thing called the black hole information paradox that says that it's inconsistent to have something governed by relativity that only cares about this mass thing, and then you have quantum mechanics comes in and says, oh, but you can't destroy this information, and those just they just don't agree with each other. And then when you talk about is
the theory of everything the concept of bringing those together?
Sort of, yeah. So theories of everything are theories that try to bring together particle physics and gravity in some way to make them agree, so and those are important also, not just around black holes, but like if you're thinking about the very beginning of the universe, you had this very, very dense universe, and in this very dense state, then probably at that stage, gravity and quantum mechanics were both important because it was such high density that should sort of engage both of those things. It's very small and very dense and very massive, and so like both of those concepts should come together, and we don't know how to make them agree. Like general relativity says that gravity comes about because of the shape of space. Quantum mechanics says that everything is particles and fields, and we don't have a way of talking about gravity that involves particles and fields right now.
That's so cool. And go.
I'm just like, so what is even the first step like of trying to solve that? Is it like a math problem?
I picture like Goodwill Hunting. I picture like the chalkboard,
right?
and they're like doing circles, and they're like, yeah, well, I know. When we put G in, it doesn't work.
I mean, this might be an unfair question.
Yeah,
it's like,
no.
Is it that just no one really knows the right way, or is it a question of these ways that we express them through the mathematic language or physics language is just not compatible, but there is a way, we just haven't figured it out yet? I don't know.
Well, so string theory is an attempt to fix that, right? So string theory is an attempt at a theory of everything, and that's based on a different kind of formulation of the mathematics that can produce gravity and particle physics working in a way that would be would make sense mathematically. In order to get string theory to work, you need to postulate that there are more dimensions of space than what we can experience. So it's real complicated in that sense. But also another problem with string theory is that it's very hard to test it, right? So one of the problems with theories of everything in general is that all of the experiments that we do, all of the tests that we can do experimentally, or even observations we can do in space, they agree with either quantum mechanics or gravity, and they don't present a clear contradiction. It's only in the theoretical spaces like the idea of black hole evaporation, or the idea of what goes on in the very first moments of the universe that we can't actually observe. That's where the contradictions lie. So we know there has to be some solution, because there are places that we know happen. Things that we know happen in the universe, or did happen in the universe, where both of these things have to be important. But experimentally, we can't test these things because we can't get to those extreme environments where both of these concepts are important. So the problem is that you can put together a mathematically consistent theory like string theory, but we can't test it with the kind of technology we have. We can't make the kind of high energy collisions we would need to make in particle colliders, or hang out next to a black hole and watch it evaporate. Like there's a lot of stuff that we just can't do. So the problem is that the real problem is that our experiments all work perfectly well in the context of these two paradigms that can't agree with each other. So every experiment we've done to test gravity, straight up general relativity, everything works exactly like Einstein said it would. Every experiment we do with particle physics, you get the standard model of particle physics, which is our, the sort of sum total of our current understanding of particle physics. Everything works. There are a few places every once in a while where an experiment will come up with an anomaly. Generally speaking, the anomaly goes away. Or you can do some very tiny tweak to the experiment or to the theory to wrap that up. But you don't have some like big, flashing result like, here, this doesn't work. This is where we need to, patch it all together. And we need that. We need something to not work.
You're like hoping one day something that'll show what's wrong, right?
Right, exactly. Because then if you do the experiment and, for example, if you do an experiment, you find that the way gravity works around a black hole is a little different than Einstein's theory, then that would be like, oh, okay, we need to find a theory that predicts that.
Right.
Prediction, post-diction, whatever, but we need to find a theory that would explain that. And so far, we don't have any of that to hang on to. We don't have any
to help modify those theories in the first place.
Yeah, exactly.
not to like keep hitting this, but I just like want to know, like, is the presumption then that there is a flaw in those theories in the first place, and we've just yet to understand what that flaw is because we have no like actual data to say it's ever been wrong?
I mean, it's not, I wouldn't say it's a flaw in the theories. Like every theory is a progressively better approximation to what the universe is actually doing.
Okay.
But what we think is that there's a limit to the validity of every theory we have, and we haven't been able to test the edge of that limit yet for relativity or the standard model. And in the past we've had theories where we could get to the edge of that, right? So we started with Newtonian mechanics, just the physics of a ball rolling down a hill. Everything works perfectly until you have to deal with extreme gravity, like in Mercury orbiting the sun is so close to the sun that the extreme gravity changes the way that Mercury orbits. Or if you look at the positions of stars during a total solar eclipse, you can see that the apparent positions are bent by the movement of light through the curved space around the sun, stuff like that. Or if you go really, really fast, that changes how things move because you get into special relativity territory. Stuff like that. Like, so extreme velocities, extreme gravity, that doesn't work with Newtonian physics, and that's why Einstein's general relativity came up.
Right.
So it's not that Newtonian physics is wrong. Like if you calculate, how long it takes a ball to drop from your hand to the floor,
Like
you don't need relativity to do that. But
and that's a really interesting perspective just on everything in general in science. It's like, yeah, it's not that one is necessarily wrong if we're able to use it. Everything's just an approximation, I guess, at the end of the day. And in certain
like almost like zooming out, you get to the extremes of the universe that maybe don't apply because our world isn't that extreme in some cases.
Yeah, exactly. So we, just like nobody figured out relativity when you couldn't do experiments other than rolling balls downhill.
Yeah.
That was fine. But then once you could actually measure things more carefully and see that, Mercury's orbit is a little bit strange, that kind of stuff, then you need that new theory of gravity. And that's why it was possible to do Einstein's relativity and get that new advance. But if we'd never had any data that disagreed with Newton's theories, we wouldn't have got there. And so that's where we are right now with relativity. We don't have any data that disagrees with it yet, so we don't know where to go yet.
That was such a good example. You're such a good science communicator. Like using Newtonian physics is great way to be like, oh yeah, I get that. It still helps describe it properly. It's not that it's wrong. It's just at a different scale or level. It now doesn't work. So.
And I also didn't know until reading your book that string theory is like a blanket term you say for theories that try to bring together what we're talking about, like gravity and particle physics. But I thought it was maybe like one specific theory, like when I've read about it, but it's like any theory that relies on those sort of extra dimensions or that don't pertain to the real world, or what?
Well, it's a set of theories that, so string theories are a set of theories that have in common a kind of a way of describing particles and fields and things in terms of strings in some higher dimensional space. There are other theories of everything. Loop quantum gravity is a different category of theories of everything. But string theory is not just one theory. It is there are lots of different kinds of string theory because there are just lots of ideas about it, and we don't have a way of ruling out that many of them because we just don't have the data.
They all involve more dimensions than what we actually experience in reality.
Yeah.
Wow. I love that little thing. I always carry that to like a friends on the beach when we're having some beer. I'm like, did you know? Like, cause people, string theory has like made its way into the public consciousness.
Yeah. At least.
And what I have noticed is that a lot of people think it's a thing, a theory. And I've sort of understood that like, it's a way of bringing these two ideas together with math that rely on more dimensions. But I thought it was really clear to be like, it's not just one theory.
Right.
It's a variety of theories, and it's linked to this concept you're talking about, which is that, there are these two ways, like large gravity, theory of relativity versus particle physics. I think that is just so, for something, like, it's just so fascinating to think about. Even as people who don't have physics backgrounds, it's like, I mean, obviously it's talked about a lot in your world, and I just think it is such a fascinating, like, concept.
Okay, wait.
Yeah.
So like,
Okay.
are there other dimensions? Like, what does that mean?
We don't. I mean, we don't know. We don't know. It's So okay. So
Is
First,
the other
let's define a
dimensions
dimension.
is primarily like a theoretical thing as well to help understand how something might be versus being like,
Yeah.
oh, there are other. Okay, I'm gonna let you just
Right,
describe
yeah.
what.
yeah. No. So okay. So we experience 3 dimensions in our everyday life, right? Up, down, left, right, front, back. And then there's time, which if you're a physicist, time is a dimension as well, because space and time interact with each other in weird ways through relativity. And so how you're moving through space affects how you're moving through time. And so you just say, okay, it's another dimension. You have a much bigger grid now. And you can't visualize the 4th dimension of that grid, but anyway, it all fits together. And the idea of extra dimensions is that there's more space dimensions than the 3 that we experience. And so if you were able to find a direction that was at right angles to all of the directions that we can normally experience, then that would be like our additional spatial dimension. And there could be many additional spatial dimensions.
So does that?
but-
Because I feel like the word dimension in like popular culture somehow
Yeah.
became known as like another world almost.
Yeah,
or something.
yeah,
like
yeah.
another that there's like this other
Another realm.
realm. Yeah.
Yeah. And in physics, dimension does not mean a realm. It just means it just means a direction. Basically, it just means
Right,
like a direction you can have an extent in, and so there are good reasons to imagine that there could be more dimensions of space, but we also have experiments that we can do that can kind of restrict the sizes of those dimensions or the shape in the sense that if let's say there were another dimension of space that were like infinite in every, just infinite in some direction where, we have 3 spatial dimensions right now and they're kind of infinite extent. You could keep going forever in that direction if you wanted to. But let's say there's another direction that we don't know about yet, but you could keep going forever in that direction too. You can put some constraints on the size of that extra dimension, the existence of that extra dimension, by the fact that gravity should be able to go through all the dimensions. So gravity is not limited to our 3 spatial dimensions. We might be, but gravity could go out to another dimension if that other dimension existed. And so when we test, we can test the strength of gravity on different scales. Like we can see, if you move a little bit farther away from an object, how much less you feel the gravity of that object. And so you can test how well gravity works on different scales based on our understanding of gravity, and put some constraint on how much of the gravity could be leaking into that other dimension if that other dimension exists. And so
What?
Are you ever not the smartest person in the room? Like,
I'm rarely
honestly,
the smartest person in the room. Although during quarantine I am, because there's nobody else here.
She's hanging out at the
just me.
Perimeter Institute, so they're all, you know what I mean?
Everyone's
Like,
smart.
Oh yeah,
Yeah,
no,
no.
this Perimeter Institute is wild. There are a lot of really talented people there.
Do you feel though like when so obviously you're like an expert in your field and I feel like, oh my gosh, you're so smart. Do you get that feeling when you talk to people in other fields, or are you just what I
yeah.
mean? Like okay.
No. I mean, it's always like, everybody. I always find it fascinating to hear what other people know that I don't know, right? And
Right.
and I think
Okay,
I mean,
good. So you're human.
smart is a weird concept anyway.
Yes.
Like
yeah, okay.
you know.
I have a direct question about this
Yeah.
because I also, again, all my understanding of physics is literally through probably all these books by people you literally know
Okay.
and can have actual conversations with. Mine's all based on analogies being told to me from really smart
Okay.
people dumbing it down. But I really think there's something fascinating about art in relation to physics because I think in many ways it's not able to be described. Like, okay, so there's that concept of like Laplace's demon or something, which is like I've heard it as like, it's sort of if you had something that was smart enough or had enough information, it could predict like where every, particle would be in the future or whatever. I don't know if this is necessarily true, but like the idea that like if you had a smart,
deterministic universe.
yeah, like if you had a smart enough computer, maybe it would be able to know how, let's just think of Earth, how everything on Earth was going to move into the next like second or whatever. I don't know if that makes any sense, but
Sure.
I like that could maybe define like, oh, I would know about art, quote unquote art. But there's something to me about like, like I do stand-up comedy and like the analogy I sometimes use is like, how come something could be funny in a like a bunch of people could find something funny on one day and then the next day like not find it funny. Like there's just weird things that sometimes I'm like, do you think there is an obsession with art? Do you like art because sometimes it's harder to explain? Or am I just putting words in your mouth?
Because it has that unpredictable element.
Yeah, or it's just like, you know what I mean? Like sometimes like, I don't know. I personally have been trying to figure out why I like science so much and why I like art so much and where they intersect. And I sometimes find when I'm like learning about physics, I'm like, it's actually not explaining this other thing that we're all so obsessed with. But maybe it's just psychology, maybe it's just neurons, but I'm just curious like what you think about or if you have a respect for art and like I don't know.
Oh yeah, no, I do have respect for art. I think so. I was reading about something the other day about like what makes us feel joy, like what's delightful, right? And I think maybe I was listening to a podcast. I don't know. But one of the things they talked about is like we like the feeling of being surprised with new knowledge, and that's a pleasurable thing, right? And I think that is something that you get in both art and physics or any kind of science, is that you get that moment of being surprised by new knowledge. Like you learn something and you have this moment of like, oh, I understand that. That's really cool. You know, or you have some new perspective on something. And that's a good feeling. That's something that makes you just fundamentally happy. And with art, you get a similar thing, right? Like you see a painting that depicts something in a way that you never thought about before. You see a new detail in something that you hadn't noticed, or even, you know, music. You hear a progression of notes that tweaks something in you, and you have an unexpected feeling in response to it, or whatever. Like you get that moment of surprise and a new way of thinking about something. Kind of maybe not knowledge exactly, but a new thought, a new perspective. And so I think that both of those things can be very pleasurable in the same way. And we can approach them in the same way.
That's a really cool way to talk about art too, because a lot of people have a hard time defining, you know, everyone says it's subjective, or why is it maybe more enjoyable? Why would a song be enjoyable to mass amounts of people versus less? But it's like, that's really interesting to think about, because I wonder if things that are more exciting to more people are actually able to teach people, you know, have that moment with more people based on specific things. Like there's just a very cool way of describing it, again, from someone who's science minded. And like,
well, it makes me wonder a little bit if like, if there is just some fundamental desire in humans to have that experience, that joy or that glee, and then that is what drives people to do both of those, art and physics, or any kind of science, right? That it's like we are actually just searching for like those moments in our life.
Yeah, no, I definitely, you know, and every physicist I've ever talked to, when they're asked to describe like what they like about physics, it's always the moment of discovery thing. It's always like, you know, that moment of like, I understand this thing. And sometimes it can be like, I'm the first person to understand this thing. And that could be really cool. That's rare. That's really rare.
Yeah.
But even I understand this for the first time, or I understand this thing that I didn't understand before, and now I'm able to do that. Like that's the thing that's so cool and exciting and just fulfilling about doing physics.
So cool. And I feel like that applies to so many spaces. Like I was thinking the other day, like I've had like a lot of back problems in my life, and so I like go to some like physio trainers and stuff, and I over the last year and a half have been like working out for like the first time in my life. Like I'm so weak or whatever, but through that time, like you start to realize like there's like muscles and things that you've never really had control over, even though people go like, okay, engage this muscle, like you kind of pretend, until one day you're like, oh my god, I understand what you mean now. Like I can feel that. It's like it kind of opens up these levels when you're with something long enough that you have that moment of, I don't know, I just feel like what you're saying.
Yeah, that's my bro boyfriend knows how to pump iron. Yeah, that's the physics of pumping iron, bro.
Yeah.
Also, if you want to have any of these, if you're searching for that experience, read your book, because that's exactly the thing that I've been experiencing while reading it. It's just like, oh my God, brilliant way of describing that. Brilliant way of describing that. Like, oh my God, I've never thought of it like that. Oh my God, I've never thought of it like that. And so like, yeah, like I think that if that is, as you just did a really good sort of case study and almost advertising slogan for why you should read your book.
Well, I mean, talking about the book, can we talk about a little more of like the ways that the universe may end? Like perhaps if you have like a favorite. We don't need to like spoil the whole book.
Yeah,
and
no,
give it all
let's
away.
stick to like which one. I think I even asked you this again at this party we were at recently. So funny. I'm like,
Well,
so
recently being like not recently, but
no, we hung out with.
I'm just like,
It was
I'm
6
just
months
letting people
ago.
know like we're
Yeah.
not hanging out during.
Oh,
COVID.
yeah.
It was
Pre-pandemic,
like, it was
pre-pandemic.
January.
It was
right?
January.
Yeah,
You're
yeah,
right. That was
January,
recent. I just want
January.
people to know that we're
I
not
mean,
hanging out.
the pandemic, it was coming, but we'll admit
Yeah.
some ignorance. We were still having fun, and we didn't really think.
Yeah.
We didn't predict. Anyways, I feel bad because I'm like, I wonder if I'm like, did people do this to you at all parties? But I was like, so how do you think the world's gonna end? I literally asked you this. Like, of all of your theories,
Yeah.
is there one that you just go to bed at night? This is the one I think.
So there's the one I think is most likely, and there's the one I think is most fun. So
Ooh,
Can we hear
okay.
them both?
If you're willing
Yeah.
both, if not, you can read one. You
Absolutely.
can leave one as the
No.
pick up the book.
So the one I think is most likely is the one that's like the least fun by any, I don't know. It's less. It's not the most painful, but it is the least kind of exciting in some sense.
Right.
So
I think I know what you're.
some
gonna
of them
say.
are painful. So the heat death is the one
Yeah.
that's considered to be the most likely end of the universe. And the way the heat death works is people sometimes call it the big freeze as well, but it's the heat death is like the more technical term for it, and I'll explain why. But what happens is the universe is currently expanding, and the universe is accelerating in its expansion. So galaxies are getting farther apart from each other. There's more and more empty space all the time. And what that means is that over a long enough period of time, everything is speeding up and moving away so fast just from the expansion of space. Nothing's really moving, but like the space is getting bigger, that eventually we will not be able to see distant galaxies anymore. Like we have a little group of galaxies called the local group, and that'll be, we'll all hang out. We'll kind of come together at some point as one big blob, but we won't be able to see galaxies beyond our local group. The rest of the universe will be dark. And then over time, because there are not galaxies coming together anymore to, crash gas together and make new stars and all that, there's going to be less star formation. The gas in our universe in our galaxy will be used up, so we won't be able to make new stars here. The stars we have will burn out. So our galaxy will get dimmer and dimmer, and then like there will be black holes, and the black holes will evaporate, and so those will kind of fade away, and then matter decays, and then eventually you have this universe that's basically just cold, dark, and empty forever. And that's the heat death. And it's called
Why
the
is it
heat
called
death.
the heat death?
It's called the heat death because heat is a term for disordered energy in physics. And basically what happens is the universe just becomes like all that's left in the universe is a tiny amount of like waste heat from all the processes of the world, the universe.
Is that the most likely one because of like entropy, and that we see that entropy is kind of always increasing?
Yeah, exactly. So
so
it's
it
the second
feels-
law of thermodynamics. Yeah. So this is this idea that entropy or disorder is increasing all the time, and so everything decays basically, and you lose, you kind of lose energy to waste heat, and just in the same way that a machine will lose energy to friction, all the processes in the universe lose a little bit of energy through waste heat, and it gets distributed through the universe. And so at the end, you've reached the maximum entropy state where the universe is just this disordered energy, this waste heat from everything. And once that happens, like nothing else can happen because you've reached maximum entropy. The second law of thermodynamics says that entropy only increases. So once you're at the maximum, entropy can't increase anymore. You can't build anything, or like nothing more can happen because you would have to, you would have to increase entropy to do anything really. I mean, there can be little blips of, like sort of random fluctuations of things seeming to happen and then decaying again, but that the universe is done at that point.
I don't know. I find that one a little bit painful. I can't
not, like,
even
physically, but, like, emotionally
imagine
painful.
why
Oh, yeah.
there's other ones that are more painful.
Yeah. No, so that one's not painful in the sense that, like, I mean, freezing to death is not particularly painful. Like, you just like it's
Right.
just everything
It's
just
like a
kind of
slow-
decays,
Yeah,
right? It's
yeah,
slow.
yeah,
It's slow. Whereas you can have things like the Big Crunch, where the universe compresses and crashes everything together, and then everything gets on fire, right? That's painful.
Okay, wait. So what's the most fun one for you?
Okay.
She
Need a sip of water.
she sips and
Wait,
takes a sip of water.
I have a question
Yeah.
before. Yeah, she's like, okay, raise your hand.
Yeah.
I have a question related to that. Okay, so in that universe of the heat death, it's just like
Yeah.
very expanse and cold, and not much is happening.
And wavelengths flatline, kind of.
Basically, yeah. I mean, all the radiation gets stretched out.
Like
I mean,
energy
there's
is-
still, yeah. There's still a little bit of there's still like a little bit of background energy,
There's a
but
little
it's very
buzz.
low. Yeah,
Just a little
yeah.
buzz.
There's a yeah.
But okay, my question is, and maybe this is like, hopefully this is not a stupid question, but there's no such thing as stupid questions, that you
No.
can ask it. Okay, so like at the beginning of the universe, I just have this hard time understanding, like, what was before that. Is it anything related to what it would be like when we have a full heat death and there's nothing? Or like, it's so hard to conceptualize, like, what is there if there's nothing?
Maybe it hits the ends, then it starts shrinking again.
Well, so you need the bounce chapter, because that's the chapter that discusses universes that like restart. Okay. So there are ideas where you could have a new beginning after a heat death. There are some theories where
I like that one.
during a heat death you could have a quantum fluctuation kind of thing that would produce a new universe in this sort of empty state. There are some ideas where you have a kind of a big crunch and then a big bang, and you have a cycle over and over again. And I go through a few of those ideas in the book. So there are some ideas out there. In our kind of standard cosmology, the one that starts with this inflationary phase at the beginning and a heat death at the end, we don't know what would have happened before inflation, and there are ideas where you can have that inflationary phase in some larger universe where there's that's kind of going on forever into the past, and then a universe will kind of drop out of the inflationary phase and be a normal universe, and then die in a heat death, but somewhere else in the universe another universe just kind of pops out of that. So there are lots of different ideas for before what we think of as the beginning.
Right.
Oh my god, it's like turning me on.
Great.
I'm like, this is crazy. So it's like there's a there. Okay, so technically, according to those theories, it's like there could be another universe
That were within our
that's
universe.
sort of
Like,
doing its own thing, whether it's its own heat death, and then ours just like a little extension off of that.
Yeah.
It's like, oh wait,
Okay, that
I
actually-
can live with that.
Well, it also helps because I feel like I have a really hard time understanding, and sometimes it's been pitched to me that before the Big Bang there's nothing, but then it's like, how did? I mean, I guess that's the
depends on-
essence
yeah.
of like the question of how did like anything come to exist?
yeah, it's actually the
Yeah.
biggest question of life and our time.
Yeah, I mean, it depends on what you think the beginning was. Like, if you think of a singularity beginning, then people often say, well, a singularity, it contains all of space and time, so there was no time before the singularity, so time doesn't have a meaning. Before doesn't mean anything, and there are models of cosmology where you kind of have a singularity popping up out of nothing, but because we don't know if the singularity even happened, you have this inflation phase where we think that probably happened, although we don't know, and there's models that don't have that. Then before that there could be all sorts of different things that could have happened, and we don't really. It's really quite hard to come up with to figure out what did happen before that inflationary phase, and that inflationary phase was very early on, so that ended at like 10 to the power of minus 35 seconds, something like that. I mean, it was real quick, whatever it was. That was very, very early, but we don't know, if there could have been other processes happening before that, if we could have come out of another universe, if there was something totally different. Like we just don't know right now. But some of these cyclic models where you have cycles from Big Bang to heat death or Big Bang to Big Crunch and over again, those kinds of things, those are sort of built to give an idea of what might have happened before.
Wow. You actually just asked Katie one of the like biggest, hardest questions of our time, and she answered it
without like pausing and stuttering.
I answered
once.
by telling you that we don't know. I mean, that,
yeah, but you're like, but we do know up
very
till
eloquently.
0.0000000000034 seconds. Okay, the fun one.
Okay, the fun one.
Slash
Okay,
the
so
painful one.
the fun one is vacuum decay, which I alluded to earlier. And this is one it's been getting a lot of attention since 2012, because that's when the Higgs boson was discovered at the Large Hadron Collider.
Oh my God, I thought you were gonna be like, that's when the Mayan calendar ended, and I was gonna be like, what? No.
So the Higgs boson is kind of the final piece of the standard model of particle physics that I mentioned before. This theory of how particles and fields and everything interact. And the Higgs boson is a particle associated with the Higgs field. Okay, the Higgs field is this energy field that just pervades all of space, and it's called a scalar field, which means that it just has one value everywhere. So it's not like an electric field where it's got like a direction. It's a scalar field, so it means it's just a field of energy, and it's got some energy value at every point in space. So if the Higgs field exists, which we think it does because we've seen this Higgs boson, which is a particle associated with that field, then the value that field has is kind of connected with how physics works, how particle physics works in our universe. So if that field had a different value, and it did have a different value at the very early universe, then particle physics would work differently. You'd have a different set of particles, they'd interact in different ways. And so you'd have a kind of different constants of nature and all of that. Just physics would be a different setup. And so the sort of value of the Higgs field tells you that you're in a certain kind of vacuum state. Now, vacuum state means the state of physics in the universe, like how physics works in your universe. So we know that we had a different vacuum state in the very early universe, and then there was an event called electroweak symmetry breaking, which I talk about in the book, and I worked real hard to make that not complicated. And then now we have our current vacuum state. So the problem is that it's possible that the Higgs field could change again, and if it did, then we'd be in a different kind of vacuum state where our current physics of, particles that work together and become molecules and all that wouldn't be able to happen anymore. You'd have different laws of nature, different like particle physics, and all structure would be destroyed, right? So you don't want to be in a different vacuum state than we're in. We like being in the one we're in.
Yeah, please, I want to stay here.
Yeah. Unfortunately, when we discovered the Higgs boson, that told us something about the Higgs field. And what it told us was, based on our current understanding, the current vacuum state we're in is not the most stable possible vacuum state. It means it turns out that our vacuum state might be what's called metastable, which means it's stable for now. Like we're cool for the moment. But it could at some point change. And the way that would work is somewhere in the universe, something would happen, and the Higgs field at that point would change to this other vacuum state, the so-called true vacuum.
It's true? No, I want ours to be true.
I know, right? No, it's bad if we're not. We're in a false vacuum. That's what we're seeing.
Oh, so that's a harsh word.
I know it is. It's terrible. So you'd get this true vacuum state started at this one point in the universe, and that would create a bubble of the true vacuum. And that bubble of true vacuum would expand through the universe at about the speed of light. And first it would destroy everything in its path, because it's got like this bubble wall that has some energy associated with it. And then once you're inside the bubble, because the bubble wall passed over you, then your particles don't hold together anymore, because particle physics is now wrong, right? Like you now have a different
Oh my God,
physics.
the 2020 memes. If it happens this year, we won't even be able to meme about it.
No, because you won't see it coming, right? Because because it happens at the speed of light. And if something's coming at the speed of light, you can't see it coming. And then, but you also don't feel it, because your nerve impulses don't travel that fast.
Yeah, like,
so
I'm
you
kinda
kind of
into
don't
that.
notice it. And then, yeah.
Oh no, go. And then what? I'm like, please end with like, and then you come back to life and you live and you're happy. No.
Well, unfortunately, it seems that so if there is this true vacuum possibility, then it's at a higher value of the Higgs field, which means that it's a kind of space that's like gravitationally unstable, which means that after you get incinerated by the bubble wall and then your molecules get torn apart by being inside this wrong physics space, then the whole space collapses gravitationally into like a black hole. So it's a very complete like destruction of the cosmos if it happens. Right. And so discovering the Higgs boson, because we learned a little bit about the Higgs field at the time, that suggested that we're in a false vacuum, that a true vacuum is possible. And so now people talk about this, but then you might be asking, okay, what could make this event happen? Like what could make this happen?
Triggers it? Yeah,
what triggers it? And so there are two answers to that. And one of them is just like a high enough energy event basically could trip the Higgs field into this other state.
No.
But fortunately, it's impossible to reach those energies. So you can't actually do that. Like certainly particle colliders can't do it. Nothing in space, none of these processes in space, which are much higher energy than particle colliders, nothing seems to be capable of doing that. There's a little bit of caveat to that when it comes to small black holes that probably don't exist. So that's a detail.
The small black holes that barely don't exist. Move on.
Whatever. Yeah. I have to mention that because I wrote a paper about it. But anyway, so basically it's like if you had a. So one of the ways people often describe it is like you have there's like a big valley and there's a little divot in the side of the valley and you're like a pebble sitting in that little divot in the side of the valley, and so you're okay if there was enough if somebody came along and bumped you, they could bump you out of that divot and you could roll down to the bottom of the valley, and then that's bad, right? But as long as you're in that little divot, you're okay. And it seems like there's nothing that's powerful enough to knock you out of that divot. Like the wall of the divot is too high. But then the problem is that we live in a universe that is governed by quantum mechanics, and quantum mechanics says that sometimes things can travel through solid walls without having to pass over them, right? So in quantum mechanics, you have quantum tunneling, which is where you can have a barrier, like a sheet of metal or something, and you have an electron on one side of that sheet of metal, and it doesn't have enough energy to go over, or like you're not moving it at all, but every once in a while it'll just kind of materialize on the other side. This is called quantum tunneling, and it happens all the time. Like in electronics, we use it for certain kinds of microscopes, and it happens in like flash drives and all these kinds of things. Like quantum tunneling is just the thing that happens on the quantum scale. Things can sometimes just move through barriers. Unfortunately, it applies to the Higgs field too. So you're
the little jump. Yeah. It's just like goes through.
This little pebble in a divot can just tunnel right through that divot and end up rolling down the valley, right?
God.
So that's bad. So the reason that's bad is that quantum tunneling is the sort of thing that you cannot predict, right? It could happen at any moment. What you can do is you can put some kind of number on like the decay rate, just like with radioactive decay. You get a half-life that says that by a certain number of years, half of your material will have disintegrated, but you don't know which half or anything like that. In any particular atom, you can't say when that one's going to decay. It's the same with the Higgs field. So we know that based on current calculations, that half-life kind of number, the time it would take for this bubble to form spontaneously is something like 10 to the power of 100 years. So it's a very long time.
Okay.
Very long time from now. But that said, it could happen at any moment, right?
Yeah, and I was like, oh my God.
It's just very unlikely. But then
if that happened in like a really far, far away part of the universe, then it would also just take a long time to get to us as well, right?
It would take,
It technically could have happened, and we're just waiting for it.
I mean, according to our understanding of the standard model of particle physics, it'll happen eventually. Like if you leave the universe alone long enough, it'll happen. But you can take comfort from a few things. You can take comfort from the fact that nothing you could do about it if it were happening. Also from the fact that it's painless, you wouldn't see it coming. It's not scary. You probably wouldn't really notice in any way that means anything. Nobody's going to miss you. The whole universe goes. There's no FOMO or anything
Pretty
like that.
fair.
Like, it's not,
no FOMO. I have bad FOMO.
FOMO is like that's the true bad ending.
Yeah. But then also, like, we know that the standard model of particle physics is incomplete because we know that it doesn't work with gravity. That it doesn't work with dark matter, which is this sort of mysterious stuff that's most of the matter in the universe, but it's not accounted for by the particles we know about in the standard model of particle physics. So we know that model is incomplete. So maybe when we find the complete story of particle physics, it'll say, actually, we're not in a false vacuum at all. But we don't know yet. So we're trying to figure that out.
Oh my gosh, what a great hopeful ending. But I also love how you started by being like, well, here's some things that are good. This will be some hope for you. Okay, you can't control it. And you would just instantly die along with all your friends and family. Which is great.
Well, very hopeful. You shouldn't worry about things you can't do anything about, right?
Yeah,
like,
and
whatever.
also you kind
life
of
lesson.
Yeah, you talk a bit about it in the book, which I think is true, which is like, if you have a dream of writing a screenplay or something, write your do whatever, because like we all might just get obliterated as we go to the true, not the false version of whatever we are in right now. We are false. Oh my God. Okay, we definitely have to have like another podcast that you come on and you talk about dark matter, because we didn't even get into that, and that's another thing that I'm so interested in. Whenever I read, I'm like, say what? But like before we end, I'm just like, what do you like, how do you, I mean, maybe this is so natural for you to speak about these things and think about these things. But for me, even like, I love this so much, but I know like after this, I'm going to like, I don't know, like do something to bring my brain back down to earth kind of way. Yeah. I wonder, do you feel the need to do that or not? Maybe you're just so used to it. And if you do, how do you do that?
Yeah. I mean, sometimes, So if I'm really engulfed in work, like engrossed in my work, which happens very rarely lately because it seems like there's always emails or something happening. But when I get really engrossed with my work, it does sometimes take me some time to like remember how to talk to people. So that's definitely a thing. As for how I deal with that, I don't know. I do a lot of I consume a lot of science fiction, which is, I like science fiction about spaceships. I read books about spaceships. I watch TV shows about spaceships. I enjoy that a lot, and that definitely can help sort of reset my brain.
Is it always spaceships? Like what science? I love science fiction, but I kind of like weird, like almost like apocalyptic climate change, like not that far in the future type.
I find that so stressful.
Yeah, me too. But it makes me, I don't know. Yeah. What sort of science fiction do you love? I
mean, so the reason I say spaceships is because I figure if it involves spaceships, then it's futuristic enough that it's definitely escapist. It has nothing to do with my life. So I don't know. I mean, I like a lot of different kinds of science fiction. Not everything I consume does involve spaceships, but sometimes it involves time travel. That's fun. But yeah, I don't know. I really like all the Star Trek shows. I really love the TV show The Expanse. That's great.
What's that about?
And it's about a civilization where there are people living on Earth and on Mars and out in the asteroid belt, and they have like all these weird sort of conflicts and stuff. And then there's this sort of alien threat, and it's very good. It's very good. Yeah, I think
I've never watched Star Trek, and I feel like I should, and I feel like I would love it.
Do you like the new one?
Picard? Yeah, I like all of them. I've never seen Enterprise. I've seen all the others. But I'm rewatching Deep Space Nine at the moment, which is fun.
Ooh, and Battlestar Galactica you talking about earlier.
I liked Battlestar Galactica, yeah. That was great. And yeah, so I love those kinds of things, like everybody's traveling around in spaceships in the future.
All right, no, that's cool. Do you think we're gonna get off this planet? Oh, I'm just still throwing you like really tough questions. Do you think we're gonna make it
like end up having like permanent habitats on Mars or whatever?
Yeah, well, I just find it, another thing your book made me think about was, like you do mention that we are like the sun will engulf the Earth. Like, you know what I mean? Like, so there's that's almost like a micro.
We do have We do have a time limit. I mean, it's 1 billion years, but
and it's like a micro scale, like in the way that you talk about everything. It's sort of funny that like that becomes small. That I'm just like, do you think we'll escape that?
I don't know. I really don't know. And it's very hard to say. I mean, who knows what's going to happen in 1 million years, much less 1 billion. I mean, 1 billion years is around when the Earth will get so hot from the sun getting brighter that the oceans will boil off.
Yeah.
It takes a little longer for the sun to actually engulf things, but just the sort of but I don't. Yeah, I really don't know. I think it's possible. I think it's very possible that we'll find ways to live in space. But it's really hard, and it's not something that we can easily do now. I think people talk a lot about like, oh, we need to go to Mars so we have a backup planet and stuff like that. Like, there's basically nothing you could do to Earth that would make it less habitable than Mars, right? I mean, you throw an asteroid at it. You could, horrifically horrible climate change, nuclear winter. All those things are way more survivable than Mars.
Oh, that's an interesting perspective. Yeah,
I mean, because if you go to Mars, you're living underground in this hostile radiation environment with no, like a very thin atmosphere with almost no oxygen. The soil is toxic, right? Like you have less solar radiation. Like, just everything about it is unlivable. I mean, it's cool because
there's no Twitter. It's like, what?
Right? Yeah, I mean, it's a cool place. Like, I want to go. It looks amazing. And it's the closest we have to Earth, but it's also like everywhere on Earth is easier to live in than Mars, and virtually anything you could do to Earth, short of like hitting it with something the size of Mars or whatever, like almost anything you could do to Earth,
right?
Is not going to
worse.
Yeah, wouldn't make it worse. I mean, we have a global magnetic field that alone is really important. So
I love our global magnetic field.
It's really good. Yeah, it's
really
so helpful.
good.
It's so helpful.
Katie, thank you so much.
Wait, where can people get your book?
People can get my book at whatever bookstore they
all
they
over the
prefer.
place.
Yeah.
Online,
There's
in stores.
Yeah, so check out your local indie sellers. You can look for it on Amazon. Barnes and Noble, all those different places.
And then where can they follow you?
You can follow me on Twitter. I'm AstroKatie on Twitter. I'm on Facebook at facebook.com/AstroKatie. And I'm on Instagram, and I recently got a new handle on Instagram. It's AstroKatie Mack. Because the handle AstroKatie was taken, and I can't.
Oh my God, give it over.
Yeah. I keep writing to the person who has the handle and being like, please, and she just ignores me and then posts.
Maybe send them one of your brilliant.
She actually posts pictures of, like, she's active. She's like actively
sort of. She wasn't for a number of years, and then she turned on, like, she started using it again, and now like anyway.
You just look at her photos every day, like, no.
I mean, I'm sure she's a wonderful person. I don't want to don't go like harass her. Or
yeah. No dogs
but,
on Instagram.
But anyway, so AstroKatie Mack is my Instagram handle.
Awesome.
So those are
the book is incredible.
Sorry.
No, go. You have something to say. I was just going to go off about how great you are.
I just wanted to say my website, astrokatie.com, has book information and all the social media and stuff.
It's such a great book. You should be so proud. It's
Thank
like,
you.
obviously from this conversation, people can understand how intelligent you are, but I think it takes an incredible intelligence to make this type of stuff, something
accessible.
that we can absorb. And I really think that this book is so amazing. And I haven't finished it, but I cannot wait to literally like hang up this call so that I can continue to go read it. Like, it's so freaking good. And I just like hope you enjoy, because I know releasing art and science can feel weird, but do your best to just take it in because it's so incredible.
Thank you. I really appreciate that. I'm really glad to hear that you like it. It's at the stage where very few people have read it so far. So anybody saying they like it is like, ooh, it's actually good, baby. Yay.
Yes, it's so good.
It's great.
And it's just about the end of everything.
Yeah.
Wow.
Amazing topic to learn about. Well, hopefully we can have you back on sometime because I do feel like there are so many other things in physics that we do not understand and would love your help understanding.
Okay, yeah, I'd love to come back and talk about dark matter or dark energy or whatever.
Yes, please. Okay,
Amazing.
thank you.
Well, for everyone listening, you can use the hashtag #SideNotePodcast to chat about us, to let Katie know what you think your favorite ending of the universe is. Otherwise, we will talk to you guys next week. See you later.
Bye.
Thank you.